I'll go ahead and hit record since it's almost time.
Do you want to wait for Daryl or?
Yes, we can wait.
Oh, he's here.
Is he already here?
Yeah,
Excellent.
just this moment.
Excellent.
I'm sorry, we didn't offer it. We don't offer anything. Maybe next semester. Okay. So I guess I'll start from the really brief introduction. Can you click on the?
Yes, I clicked on record.
So this is our first physics seminar of the semester. Unfortunately, we only have 2 of them because of some scheduling issues. So, but I want to say this: so if anybody that's kind of interested in joining the physics club, we have a society of physics student here. Unfortunately, the chairman and then the president and vice president both missing. And so I'm just saying on behalf of them that if you're interested, you can join for free, and we'll do activities. Well, we haven't done anything last year because of COVID, but before that, we used to have some other activities. Besides this kind of seminars, we have like activities like we had a tour to Tulsa, to some like flight. We used to have one tour to flight safety, the company, and then I think we have another tour to like OSU physics department. And then we have another tour. So I mean, we can do things like that, So if you're interested, feel free to let me know. I can let them know. They will put you on the list. And so anyway, so today we have our, familiar like Professor Matt.
Am I our first speaker of the semester?
Yes.
Okay, good.
Yeah. Dr. Buckles, and he's going to talk about n equal to np. I guess there should be supposed to be a question mark there, right?
Yeah, sure.
P equal to np,
Sure.
and the problem in computer science and also in math, it's a very interesting problem.
I'm pretty sure it's a math problem. But anyway, it's considered a computer science problem too. Okay, so this talk is about 2 what are called complexity classes for problems. And the first problem is the P plus problem. Okay, so the first thing you have to know is that these problems are always in the form of decision problems. They're problems that have like a yes or no answer. Can you guys think of any math problem that definitely has a yes or no answer? It's not so easy, right? Do you have an idea?
Like is 2 integer, that one, that kind of thing?
Well, right, sure. Okay, that one's pretty easy. Is 2 an integer? Well, do you guys know the answer to this one? Yes. Okay, pretty obvious. Now a harder problem would be something like is the number 7,000 72,911 prime. Okay, do you guys know the answer? Happen to know the answer to this one? Probably not, right? Okay, so
yes,
so it just so happens that it turns out the answer to this one is yes. You can imagine if you tried to program a computer to figure out this answer, how long would it take, the computer to figure out the answer? That's kind of what this P is about. It's all about, can you write a program given this input, 72,911, that can kind of quickly determine if the answer is yes. Now, how you write the program is up to you. You can write it in a sophisticated way. You can write it in a simple way. Can you guys think of a simple program, a strategy that a program could use to figure out if 72,911 is prime? What's like a simple way to try to get a computer to figure that out?
Method of exhaustion, just divide this number by.
Yes, you just divide the number by 1, by 2, by 3, by 4, by 5. I guess you'd start at 2, right? And you're trying to figure out, is there something that divides evenly into the number? If there's something that divides evenly into the number, then the answer is no, it's not prime, it's composite. But if you try a lot of numbers, eventually you might exhaustively figure out, oh yeah, it's prime, there's nothing that divides evenly into it. Okay, now another problem. So here's another decision problem. Have you guys ever seen Okay, so have you guys ever seen this puzzle where you basically have a lot of pegs and you can use pegs to jump over, other pegs? Where have you seen this problem?
I was gonna say Cracker Barrel.
Yes, that's what I was gonna say, Cracker Barrel, but this is also Denny's, this little puzzle. Okay, and do you guys happen to remember how many rows of pegs that there are in this problem? You don't remember. Okay, so probably the one you've seen at Cracker Barrel is probably like 5 rows. Of course, there's no reason why you couldn't add like more rows, so online you could definitely find, commercially produced versions of this problem that have like 6 rows. So you could ask a computer to try to figure out, is there a solution to this particular puzzle? And it's like, in this case, if you had to guess with 6 rows, do you think there's some way to jump over pegs? Jump over pegs and then you remove them, and you just keep jumping over pegs, and you're hoping to have 1 peg left. You don't really care where it is, or anything. So do you guys have a guess as to whether 6 rows might be solvable, something at that level of complexity? The 5-row one definitely is. Maybe the number of rows have to be on, right? You see, it's actually a pretty hard problem, right? You have to try a lot of different ways of solving the problem. It would not be easy to even program a computer to try all the ways, right? But that's kind of what you might do. You might solve this one by exhaustion. You might teach a computer the rules, and then you might have the computer just systematically look through all possible ways to win. And if the computer can find a way to win, the computer should tell you, yep, there's definitely a way to win. So the solution is yes. Now, it turns out that 6 rows is solvable. They do commercially make this puzzle. So I've never solved it myself. I never was smart enough to figure this one out. But anyway, so it's not really that easy of a puzzle. Okay, now something that would be like not a decision problem would be something like, what is the factorization 2,160. Okay, so if you try to factor this as a prime of primes, well, it's an even number, right? So that means it has a 2 as one of its factors. If you divide by 2, do you guys know what would be left over? 1080, is that divisible by 2? Yeah. If you divide 1080 by 2, now you'd be left with 540, right? If you divide 540 by 2, 270. If you divided 270 by 2, 135. If you divide 135 by 3, how much? 45. If you divide 45 by 3, 15. If you divide, I'm outside the bounds. If you divide 15 by 3, 5. Okay, so what's the factorization? This is 2 to the 4th times 3 to the 3rd times 5, right? Now that's not, you could ask a computer to try to solve this problem for you. You could write a program to solve this, but this is not considered a decision problem because it has to give you like a lot of answers, right? The program would have to tell you there's 4 2s, there's 3 3s, there's a 5. It's a lot of information the computer would have to give you back. So this kind of problem has nothing to do with this, well, nothing obvious to do with this P plus of problems or this NP plus of problems, because those are just in terms of like trying to solve the decision problems. Okay, so let me give you guys the formal definition of the P class of problems, and then try to spend some time explaining what is the meaning of the formal definition. So, and I'm saying it's a formal definition, it's almost a little informal too, this particular first definition. So roughly what it is P is the set of all problems. This is kind of the imprecise part. That a computer program could solve. In polynomial time. On the size, or I don't know, maybe it's in the size of the input. Okay, so the input represents the coding of your problem you're trying to get the computer to solve. And if your problem becomes more and more complicated, your computer is going to be allowed to have more and more time to solve it, So for example, well, maybe I'll give you an example of it, but that's roughly the idea. Do you guys know what a polynomial is? It's like, what's an example of a polynomial?
Like x to the 3rd plus 2x plus 7.
Right, and so you don't even have to get this complicated, you could just say, if the input has size, let's say, 2, then if this is the polynomial that bounds the running time of your program is allowed 8 units of time to solve the problem. If your input size has size 4, 4 to the third is 64. Now all of a sudden you're allowed, 64 time units to solve the problem. So basically it's like your program has longer and longer to solve the problem as you input versions of the problem, which are more and more complicated, like larger and larger primes or larger and larger puzzles, But as the problem becomes more complicated, you get more time, but you still want it to be the runtime of your program to be bounded by a polynomial. Now you're allowed for the polynomial to be very, very big. Like for example, the polynomial could be x to the 6 times 100. Well, by putting 100 there, you're giving yourself a lot of time, right? And by putting an x to the 6 there, you're like, yeah, I'd like a lot of time. But this is real different than if you allow yourself 2 to the x or something that grows exponentially. That's giving yourself too much time to solve the problem. So the P class is like, can I solve it on a computer? Kind of in a reasonable amount of time, but reasonable in their definition is bounded by polynomial that says input. Okay, now what is the set of all problems exactly? Well, I need to define that way more precisely, so we'll do that later. But okay, then there's another class called NP. This is the set of all problems that can be solved Wait, did I even use a complete sense here? Set of all problems that a computer, oh yeah, I did. Okay, that a computer program that is non-deterministic. I could solve in a polynomial the size of the input. Okay, so this stands for non-deterministic polynomial time. So I have to explain to you guys, like, what is a program that's non-deterministic? Because in the real world, our program's entirely predictable once you start them running. Yeah, they're supposed to be entirely predictable. So for some reason, this non-deterministic program is some other kind of program type, but maybe it's non-predictable or something. But it seems like it's almost the same concept because you still want this non-deterministic computer to be able to solve the problem relatively quickly. So this question of, is this really the same class of problems, is really asking, is a non-deterministic computer in some sense does have a similar power level to just a normal computer? It's a real weird way of studying it, but I need to explain, like, what are the two types of computers? So there's the computer Okay, so what's the concept? A computer program that they're using in this line of work. The concept of computer is kind of replaced with a slightly different concept. The concept of a Turing machine. And what a Turing machine is for all practical purposes, it's just like a computer, but there's one difference. There's an infinite amount of memory available that the machine has available to it. So you can imagine this is a memory location, it can store 0 or 1. This is a memory location, this is a memory location. And if you list all these memory locations, the memory locations go from a starting one all the way out to infinity. Okay, you imagine the computer has as much memory as it wants, right? Now that's obviously a little different than our computers, because our computers always have a certain internal memory, system memory, and it usually stops at, what's a typical amount for most computers nowadays for like their system memory?
16 gigabytes.
Right, sure, maybe they have 16 gigabytes of internal memory, then that's it. Now, the reason they need to generalize the concept of a computer is they're imagining the problem's going to get bigger and bigger, and therefore need more memory. if they don't have an infinite amount of memory available, it's like, well, now the problem can't get as hard as it wants to get. You can't, recognize its asymptotic complexity, so go out to infinity. So the machine has an infinite amount of memory, and there's also a read head. They have to have a read head. And if you want to read what's in memory, you have to manually move the read head to the right and to the left to access any part of memory. That's a little different. Normal computers access memory. How? Like a real life computer?
Access the 15th spot.
That's right. They do it by what position, right? Address. If a computer knows the address of the memory it wants to access, then it's like it can access it. This one has no addresses. It's like you have to manually move the read head right and left a bunch if you want to read its memory. Okay, so there's a read head. It starts at the beginning, of course. And then there's also a Turing machine has a built-in program. If we had a computer that just read one program, that would be kind of like a Turing machine. So a Turing machine only runs one program. It's not really reprogrammable or anything. And one way to visualize the programs, the simplest way is you can imagine that they're kind of a graph that just tells you what the program does. So let me give you an example of a program written as a graph and see if you figure out what this program would do. Okay, so this program here branches initially here, then it moves the read head right, then it branches here also. Okay, now here it moves the read head right. And it stops in this direction. Stops in this direction. Okay, so my claim is that this is somehow a way to describe a program. So if the read head starts at the very first unit of memory, any guess what I'm trying to say the program is going to do here?
Giving it like a yes or a no.
Well, yeah, basically, if you notice, this program could branch this way or this way. If it could branch this way or this way, it's probably branching because it's going to read that bit of information that's where the read head is. So anytime you see a branch in one of my programs, that just means it's going to read that information. So in this case, it happens to be reading a 0. That means the program is going to go from here to here. Now, just like there's a read head, there's kind of like when you're running a program, there's kind of effectively an instruction pointer that remembers where you're running the program at. Okay, so now it's like you go here. Okay, now there's only one arrow going here, so you just follow it. So this means now you should move the read right head, you should move it to the right. So that's going to cause this to be here. Okay, now if you notice there's branching here. So if it branches in 2 places, that means I intend for the program to read what's stored in memory. In this case, what's stored in memory now is a 1, right? Okay, so the program goes over there. Then you only have one arrow to follow, so that means you should move the read head to the right? Okay, now there's some branching here. So there's the current read head position, so that means we should go this way. Okay, and then there's only one way to go. We go here, we reach an S, that means stop. Okay, so in this case, if you were trying to solve a decision problem for which this was the input, that represented abstractly the problem to the computer, this would be the computer's returning an answer of yes to your question. That's how the computer communicates a yes or no. They just make sure to end the read head over the correct 0 or 1 to represent the yes or no response. Yeah, question, right?
No.
Okay, you sure?
I didn't have any slides. Interesting question.
You don't have a question?
Not yet.
Okay. Because you really look.
So 1 is like yes.
Yeah, so if this is like simple, whatever the read head ends over, that's the computer trying to tell you the answer. It could easily tell you yes answer is a 1, the no answer is a 0. Okay, so let me show you guys another example. See what the time's like. Oh, time's good. Okay, so let's say your program looked like this one, just to give you guys one more example here. Okay, so by the way, with these programs, the way I'm describing them, S means start or stop. How do you know if it's start or stop? It's pure context, right? The start has one arrow going away from it. All other things are stop, Okay, so S means start or stop. R means move right. move the read head right 1 unit. L means move the read head left 1 unit. Okay, do you guys know what 0 means in a program? Okay, so yeah, go ahead.
false, on.
Yeah, so if the program returns a 0, it's like false, right? But I'm saying while you're running the program,
It's just like the number in the location, right? You read the.
yes, this either means that you just read a 0, that's why you're going down that path. You're going down that path because it was a branching path and you just read a 0. Or my first program didn't have this. It can also mean write a 0. Write a 0 is like if you just run into a 0 directly without any branching. Then a 0 means write a 0. I'm just trying to use the same notation for multiple things, just to make it interesting. So you have to think about the context. So that means either read a 0 or please write a 0. 1 means the same thing. You either just read as 1 or it means please write 1. So if you notice what these programs could do, they could read from memory, they could write to memory, and they could branch. The program could branch based on what's in memory. That's literally all they could do. Do you think this program could simulate any actual computer in the real world if it just had enough time to grind through a big enough program? Yeah, does it feel like that's what computers do mostly? They just read from memory, write from memory, and branch? Do they really do anything else? They don't really do anything else. Sometimes they do stuff in parallel, but you can still simulate them. So people believe that even though this is a pretty simple way to write down a program, that it's just as powerful, in terms of what you can calculate as, any actual. Do you have a question?
What is that 1 plus 1? Like you just by just doing reading and writing. Like say you want to do some calculation.
I'll leave that as something for you to think about. Like how would you do it? It's not so easy, is it?
But there's you got to have a program basically, right? Like besides whatever in the memory, you have to have a program so that the thing knows where to go at each step.
Yeah. Yeah, you're asking how could you do 1 plus 1 with these simple? You have to do a lot of encoding to get the 1 plus 1 written in there just right. It's complicated.
Well, Turing machine only has 1 program, right?
Yes, that's also true. So
1 plus 1.
if
It's like, yep.
well, okay. But the thing is, you could write a program who knows to accept multiple inputs, and then it could be a program that's designed to add, for example. I'll get more complicated in a second, so it's more obvious what's going on. But let's just do one more example program. Can you guys tell me if your program did this, and let's say your initial memory was all set to 0s. Now, by the way, that always happens. Memory is always initialized to all 0s except possibly a finite subsegment at the beginning, which represents your input. But in this case, I'm just going to set all the 0s. Okay, so this one goes right, left, and then it branches here. Okay, then it writes to memory here, and then at the bottom it stops. Okay, so in this case, can you guys quickly tell me what does this program here do? This one program.
Make the first one 1.
Yeah,
It's
that's right. Well, it's gonna move the read head 1 to the right, but then it's gonna effectively do the inverse of that, move it to the left. So now you're where you started. Then it's going to branch, so it's reading. It reads a 0, so it goes this way. And then what does it do? It writes a 1, then it stops, so it's returning a value of 1, right? So what does this program do? It just inverts the first value, the first bit of information. That's a very simple program. So if you want to do something sophisticated, how big do you think this graph will get if you're doing something that's for humans, something for real? You can imagine it's probably a lot of details, but theoretically. Okay, now that's how a Turing machine would work. How does a non-deterministic machine work? Okay, now this is sort of like a computer. Okay, but we're going to talk about what's called a non-deterministic. Machine. Okay, so what the difference is you still have memory, you still have an infinite amount of memory available to you. That's all initialized to 0s, except for of it. So this is 230. Okay, and then you also have a single program on your non-deterministic tree machine. So let me show you guys an example. Okay, so you notice this program likes to branch in lots of different directions. And then it's gonna write a 0. This case, it's gonna write 1. This case, 0. In this case, it's gonna write a 1. Okay, then all these leaves the same. It's gonna go to the right. Okay, and then this will just copy this note here because I'm out of room. So this is considered the same as that. Okay, it's just a copy of it. Then let's say it kind of does all that again. More readable. Okay, then it's going to move the read heads to the right. Okay, then it's going to write the number 1, then it's going to stop. Okay, so if you notice, in this case, the read head starts here. So since it branches here, it's going to read a 0. But which way does it go? See, all of a sudden I'm allowing multiple zeros in when it branches. What do you think that means for a non-deterministic Turing machine?
That random choose which one to take.
Yeah, you could imagine the computer actually just randomly chooses a path, right? Or another thing you could imagine is that the computer sort of does both paths. But how can it do both paths? Because if it does, what would that even be? So what it does is, if it has 2 paths it could go, this whole machine copies itself 2 times. It copies the memory. The program itself is copied also, so it gets a copy of the same program. The only difference between the 2 machines is one machine will go ahead and move the instruction pointer to one position, keep running from there. And in the other machine, the instruction pointer will go to another choice. So anytime there's 2 or more choices, you get that many additional copies of the whole machine, and all the machines will just keep running.
So it's parallel universe, basically.
That's right. Now, if you wanted to build this in real life, you could design a computer chip that different parts of the chip, just based on its transistors, you could design a computer chip where when the program sees a branch, you can feed it one of these programs, and when it sees a branch, it gets the circuitry over here, the job of figuring out that program. It would need its own memory. This part of the circuitry could do this one. Now, there is a limitation. We don't have any limitations. Each branch, till there's millions of them. But on a real computer chip, you'd be limited to how many transistors does that chip have? And when you run out of space on the chip, you better slow down and start doing some of them and then later do other ones. And you can imagine a chip like that would have a pretty complicated design, right? Because once it reaches its maximum capacity, it's got to think how to reach its maximum capacity. But let me assure you, I've seen chips designed like that, so I know you can do it, on a chip. So anyway, so can you guys describe what this program and all its copies are gonna do? Can you guys tell what this one does? So we can just think there's different memories. So one of them's gonna, after it reads this one, it won't go this way, right? Because everything is initialized to, or that first one was 0. So one of these programs is gonna immediately write a 0, and one of the copies of the program is gonna write a 1. Okay, so like that. Okay, and then whichever program is running, they're both of them are gonna be the read head to the right by 1. Okay, no matter which one you're running, what are they now gonna read? I think they're gonna read a 1, right? Because don't all of them have a 1. Does that make sense? I put a 1 there, so they'll branch in these 2 ways. So basically, both of these will become, we'll have 2 copies. Now for this one, the program that wrote a 0 initially, now that program is going to either write a 0 or a 1. So you'll get one machine that's written a couple zeros. You'll get one machine after after so many steps that tries this. Okay, what about the program that had written a 1 initially, had come down this path? Well, that program will, branched twice, so it'll become 2 copies of the program, and then it will write a 0 to 1. So there'll be one of the programs that's running will have a 1, 0 here, one of them will have a 1, 1 there. Okay, and then the read head will, in all cases, in all those programs, will move to the right, and then this non-deterministic program will write a 1. So all of these are old news. They were the memory states of the past. All of these will write a 1, and then all of those programs will stop, right? Okay, so if you notice, in the end, there'll be 4 copies running that will have run, and they'll write different things to memory. Would it be pretty easy to write a non-deterministic program that just writes all combinations of, possible 0, 1 patterns? Just by repeating this whole process for, a few more times, and you can basically just get it, different programs to write all conceivable patterns of memory. Doesn't that seem pretty powerful? A program that can branch off and, consider lots of potential inputs even at once. They can interpret all those things as inputs. Okay, now here's the thing. We want this program that's branched off into lots of programs to give us either a yes or no answer to a potential problem we fed it, into the input. So if there's multiple programs running, and let's say they all stop, what answer do you think is the answer? You see the problem. It's like they might all be giving different answers, because in this case, what are all of their answers? They're all yeses, so I guess that probably means the final result should be yes. But what if there are lots of combinations? What if there's 1 yes and 1,000 no's? Any guess how we're supposed to interpret that result? Let's say there's one program that says yes, and then 999 other programs that say no to our problem we found
We'll
it.
just take probability. We'll take the majority rule.
The majority rule. Okay, so do you have to know how the psychology of it how it works? The way it works is if even one computer says yes, you consider all of the group of computers to basically be saying yes. What's the psychology of it? Let's say you're trying to solve this PEG problem. Do you think with a program that can branch in lots of ways, that different programs at the same time could be analyzing different potential legal moves, right? And so a lot of them might try different moves and not solve the problem. And so those ones would just say, no solution. But what it really means is they couldn't figure out a solution. So if even one guy tries some sequence of moves and says yes, you listen to that guy because that's the one that figured out. You can even look at what path he ran through and probably infer what the solution to the problem actually was, right? So, however, how many steps did this program take? You just look at whichever one ran the longest, and that's how long it took. So they're all kind of running in parallel, but whichever one took the most time, you credit that as the time length of running, for the whole system.
Is it possible to have opposite case that one no is enough to deny the whole thing?
If you wanted it to define the problem in those terms, you could have, it's just they defined this.
Where do you want?
Well, in this case, the NP class, they just defined it as using this particular way of saying. So if you can build a non-deterministic program that can solve your problem in polynomial time, then you say that problem is an NP type problem.
Another thing is, why do you measure the time, count time as the longest? Maybe when you
yeah.
yes, you stop, right?
Time to run is just count how many nodes you went through.
Yeah, but I'm saying that some branches may take longer time to figure out.
That's why for this one you have to take the maximum runtime of all branches.
But if I already got yes, I can stop right there.
No, it doesn't.
Stop. We don't have to do it.
It doesn't work that way. It's like the runtime is the length of largest branch.
You have to wait all the branches. That's all.
Even if one says yes, the runtime is considered the length of the longest branch, not the one that says yes. You credit it for how long does it take in like the worst case.
So the non-deterministic is basically just you just consume all the possibilities, right?
Yeah.
Because all the tournaments is essentially they're deterministic. There's no way to flip a coin or anything. So just you have to make a copy. You just run out all the possibilities because you have infinite memory. So you just right.
Yeah, and you can make unlimited amounts of copies.
Right.
So that's kind of why people think, well, probably you can solve problems faster on a non-deterministic Turing machine then you could solve the problem on just a traditional Turing machine. So that's the difference. What problems can be solved in polynomial time on a Turing machine versus what kinds of problems could be solved in polynomial time on this weird non-deterministic machine. Now they call this non-deterministic, but is it entirely deterministic in the way it branches? It's totally deterministic. Yeah.
And that doesn't seem like polynomial time, it's really branching, it seems like it's doubling, it's kind of like exponential growth rather than polynomial growth.
But the question of time is like, if you look at, even if the number of programs end up running is like 1024, you just look at how long did each of those programs, kind of imagine they're running in parallel, how long did the longest one take? And that's the amount of time that non-deterministic machine took.
So I think
It's kind of like you're allowed a lot of parallelism.
I think the point is like when the dominant thing, you're increasing the space, like memory, but you're not increasing time. So because they're all running at the same time. So in the end of the day, it's still like.
Yeah, if they're running at the same time, it's kind of like it didn't really take more time. Yeah, that's kind of a good way of saying it. Kind of hard to build that in real life, but it's not totally impossible to have computer chips do an awful lot of calculations in parallel to an extent, but not quite as freely as this goes. Okay, now there is a technical glitch. If I want to take a math problem, encode the actual problem as digits here, it might matter how, well, first of all, there's one really big problem, which is, let's say I input this and the rest are zeros. Is there any way for my program to even know where I intended the end of the input to be? No, what's the problem? The problem is the computer can read here, read this, read this, read this, read this. And then when it starts reading zeros, couldn't the program think that perhaps I have more data somewhere down the line? So it's like,
put it in the program, right? You tell the program.
you don't have any way of inputting anything into your one program your Turing machine's running except for this initial data segment. It's all you have available to, right? And it's like the computer simply can't tell where you're, so you can write these programs, but they can't really tell where you intended your input to start and stuff. So what you kind of need more symbols. Ideally, maybe what you do is you have symbols like 1 and 0, and then maybe when your input runs out, maybe the rest you want to have kind of like a blank symbol. And when your program hits a blank symbol, that's like telling the program, okay, that's the data. Like there's the whole problem. You can see the code. Well, if you want to do this with zeros and ones, you can make it encoding, like use 1 1 to represent this is actually a 1, 1 0 to represent this is actually a 0. You could use something like 1 1 as a code to say whether to use that code. You could use 0 0 as a way of saying if you see 2 zeros in a row, that's kind of like a blank. And you can even have a character you don't even intend to use, something like 0 1. You can allow the program itself to read and write its own little fourth character, but you don't intend to ever input that character. Okay, so you could do it that way. You could use 2-bit encodings to represent your intent, on the input to the computer. Or you could just assume that your Turing machine knows how to directly read and write 4 characters. Right, it's not that hard. You just use those symbols, in the middle of your program. So just for simplicity, we'll assume our Turing machines can easily write 1 zeros, read and write 1 zeros, blanks, and triangles. And once you start thinking like that, then you might think about something like this. If you want to know if a certain number is prime, let's say that's the problem you write a program to determine. You might input a number like 1 0 1 1, and then let's say the rest are blanks. Everything's going to be initialized to blanks except for that input. Okay, do you guys know what number this is? And what is the binary of?
I don't remember how I used to. I
You don't remember
figures, but
binary?
I don't remember.
Okay, so just refresh your binary. This would be like the ones place. This would be the t's place. This would be the fourth place. This would be the eighths place.
So it's 11, right?
So that counts for 8 plus t plus 1. This is a code for 11. You're trying to input 11 and asking the computer, can you figure out if it's prime? But this is not the only way you can input 11. You can input 11 as 1 1 1 1 1 1 1 1 1 1. The rest blanks. Okay, now in this case, I'm thinking of all the things as representing. weight of 1. I'm thinking this is 1 plus 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 1. That's like, I could input 11 like that, right? Now, what's the problem with this is if I decide I'm going to input numbers with a bunch of 1s like this, what's happening to the input size? It's growing really fast. It's growing at the input size is just equal to the number. If the number is 100, the input size is 100. That feels kind of like cheating. It's almost like I want to give myself a little extra time to, I want it to be polynomial, but I'm going to make sure those inputs grow in size real big, so I got a lot of extra time. Well, the moral to that story is, if somebody just gives you a math problem that says, is it a polynomial type problem, like is trying to figure out if the number is prime of is it a polynomial classic problem, without them telling you how exactly they're going to input the numbers, they're really vague when they say this, because you need to know the encoding to know, is it polynomial? I'm like, how are you inputting the number exactly? For example, oddly, according to the internet, this, if you input the number as a bunch of 1s, this is solvable in a runtime that's always bounded by constant times x. I don't know what, input size. I don't personally know how to get it to run that fast. I could probably get it to run in like 3 halves or a square here. I could definitely do that, but I do not easily know if somebody puts the number in unary, how to get it, figure out if it's brought that quickly. But according to the internet, that's possible, right? What if they put it in binary? Well, the number of binary digits for a number, if this is the number and this is the number of binary digits, then the input size grows kind of logarithmically, which means, when the number gets real high, you still don't need that many digits to input it, because this binary coding is highly efficient as a way of encoding the problem. Well, now somebody's like, oh, can I solve it that fast? I really feel like I'm trapped. I don't have that many, it's a huge number, but I only have time equal to, 30 bits of input times, to power or something like that. So anyway, that's one good thing to be aware of when they casually talk about a problem being polynomial time, solvable polynomial time. When they're being very casual about that, if they don't actually explain to you, like, how's the encoding work, then that's a well-defined, problem. Now, it turns out that someone in 2002 did prove that you can solve is it prime in polynomial time when the input's binary. But people knew that this was true like 100, pretty much since the dawn of computers, whereas this one was like 18, 19 years ago. Somebody finally was able to show that this way of formulating the problems in binary time. So because that input style matters so much, like, okay, what are the details of, how are you encoding your problem? It's better to just kind of think a little bit abstractly about how programs work. So if you start listing all possible inputs, do you think one of the allowed inputs would be kind of like nothing is inputted, like you just leave the tape totally blank? Does that strike you guys as input when you just get the computer program kind of nothing? You just don't say anything and let it run?
It's like empty set.
It's kind of like an empty set, right? Do you guys feel like that would be allowed input, sort of the empty set? Yeah, why not? Maybe, I mean, it's not like the program can't run, right? If you feed it nothing. So that's an input. Okay, now what's the next simplest input from that, from just giving it nothing?
0.
You could feed it a single 0 followed by a bunch of blanks. Okay, the next one would be the next simplest.
1.
Yeah, the next simplest might be like a 1. And then the next simplest would be 0, 0. The next simplest would be 0, 1. The next simplest would be 1, 0. The next simplest would be.
Well, what's different between 0 and 0, 0? The same thing.
Well, this is a 0 followed by a bunch of blanks.
Okay.
This one's a 0, 0 followed by blanks. Now, what's the difference based on your problem? Well, if it's binary input of a number, there's no difference. But if somehow you have a different problem and it means something different, it's up to the programmer to decide what does it mean. It could be the problem has become different in some way. It's up to you how to encode your own problem. Okay, and then the next simplest would be 0, 0, 0. And basically there's an infinite list of possible inputs, right? Okay, so let's say you have a program, which I'll just call program P. And let's say you intentionally choose this program so that it will terminate on all inputs, because you guys know programs could go into infinite loops and never return, right? And we're only interested with this P and NP. We specifically restrict our attention only to programs that that return on all possible inputs. And in this case of NP, return on all possible branches and on all possible inputs. They're not allowed to go to input loops, otherwise we're just not interested in that cover. Okay, so if we restrict our attention to a program P that returns answers no matter what the input, well, these answers are simply always answers that look like what? They all have to be ones or zeros. They're always returning one value, right? Okay, so are you guys comfortable with saying that therefore that program can be thought of as something that effectively is a function for all possible inputs? Into the set containing the numbers 0 and 1, right? So every program basically computes a function, right? Now, if I just randomly choose zeros and ones here, and then ask the question, can I find a program that will return that particular set of zeros and ones? What do you think the answer usually is?
Yes.
Well, it turns out most functions, simply there is no program that computes those functions. A lot of functions are simply not computable by a program. There is no program that could return, you know, any particular sequence of zeros and ones, especially if you're just really arbitrary about your zeros and ones. Let's say they're very randomly chosen. Odds are there probably isn't a program in the whole universe that could return that particular patterns of zeros and ones. And I'm just asking you to take my word for that because that's not terribly obvious, right? But it turns out not all functions are really computable by programs. So here's the way you think about abstractly. You have all functions mathematically that can exist. And then the ones that are computable by a Turing machine, those form a subset of those. These are called the computable functions. Okay, and here we're thinking computable by a just normal Turing machine. Now, what if you go to the non-deterministic Turing machines? Well, remember, if even one of the branching computers returns a 1 on any copy of the computer, then you consider the answer to be 1. But if all the branching computers, all the copies of the computers return zeros, then you consider the answer to be 0. Okay, so these non-deterministic Turing machines, don't they really just, if you have a non-deterministic program, doesn't it really just compute a function also? In the end, you can run it on all possible inputs and ask yourself the question, what function does it compute? Okay, now it's not obvious, but the functions that can be computed are the same set of functions in both cases. So if you look at all functions, and you look at what's computable by a non-deterministic Turing machine, it's actually the exact same set of functions. Why is it really the same set of functions? It's because a regular Turing machine can simulate a non-deterministic Turing machine by elaborately one step at a time looking at what every code would be, right? It'll take a long time, but it can simulate it as what's going on. So that's why they can compute the same functions, is because given a non-deterministic Turing machine, you can easily, not easily, but it is possible to make a Turing machine that simulates all the branches bit by bit and can figure out like what it would do, can return this, essentially the same functions. Okay, now in the world of normal Turing machines, then there's this class called the problems, not just that are computable, but are computable in polynomial time. Doesn't that seem like it's probably a proper subset? Like it's just some of them. These are the ones computable in polynomial time. Okay, this is by a Turing machine. Okay, now what about down here? We also have this NP class. These are the ones computable also in polynomial time. The only difference is you're allowed to use a non-deterministic Turing machine. So these sets certainly could be different, right? And most experts that have studied this problem really do think like they're different sets. But no one's ever proven that they're different. No one's ever shown that, okay, there's some problem efficiently computable by this non-deterministic Turing machine. However, the most progress that's been made on this problem is there are elements of this set. So if you look at this NP set, almost on top here, okay, there are functions that are computable by non-deterministic Turing machines. And it is known that those functions are kind of the hardest to compute functions by these fancy non-deterministic Turing machines. And there's this class of functions, and this is the class called NP complete. Okay, and they have the property that they're so fancy as functions in this world that if you could come up with even a single program that could solve these and follow over time, even if it took longer, like in this world, you might have a function that's computable at a time bounded by 40x squared. In this world, you may have to come up with a routine that could compute that same function in 1600 x to the 8th. But just because it kind of seems like it's taking a lot longer, it's still considered okay if it takes longer as long as it stays in that polynomial, kind of row. So anyway, there's a lot of problems out there which are known to be NP complete, and people have made long lists of them. And so if you want to prove these are not equal, it's good to go find one of these problems that is an NP complete style problem. See if you can find a program that could solve it in polynomial time, and if you could, you've solved the whole problem. If you can somehow prove there is no such program, hard to prove there's not such a program, but if you can prove there's no way to do it, that actually implies that the two sets aren't equal as well. So there are specific problems that are considered to completely decide the whole question weirdly, if you could prove or disprove that there exist arbitrary programs, that can solve. Anyway, that problem, if you could prove it, it's worth $1 billion. Someone would pay you like $1 billion for the solution, because this is one of the more famous, problems out there. So one problem, I'm out of time, but I could just give you real fast one problem I've worked a lot on. If you're just trying to get a sum of numbers to a specific number, like let's say someone inputs into a computer just a ton of numbers, and they ask you, can you go pick some out that add up to a particular sum, right? You can make this problem harder and harder by making the numbers bigger and bigger and having more of them and trying to add up to a bigger sum, right? So if you can prove that you can always figure out just the right subset of the numbers that add up to a particular sum, and you can do that efficiently as the size of the list grows and as the size of the numbers grow. If you could do that in polynomial time, that would be sufficient to show that these are the same equivalent, the same set of functions, basically, if you think of those as functions. But if you could prove there isn't a way, which I think there isn't a way, but if you could prove there's no way to efficiently solve that kind of problem, then that would successfully prove that those are not the same. So anyway, if you're ever on the Wikipedia or some other website, they talk about these NP complete problems. That's why people care so much about them, is because, okay, those problems could be studied really carefully, looking for something really efficient,
So in case they're not equal, which one's bigger?
Oh yeah, now, if they're not equal, it's like these problems can be solved by a non-deterministic machine, where the non-deterministic machine is just a copy of this program that simply doesn't branch multiple times because it doesn't need to. So it's like if something is programmed that solves this, you can just pretend like that program might have branched, multiple times. So yeah, so if they're not equal, this one would be a proper subset of this one. So anyway, that's your job. If you want to win $1 million, first go online. There's hundreds of these NP complete problems. Go find one, and because I can tell you they're probably not equal, try to show that no matter how hard someone tries to write an efficient program, they're not going to be able to do it. Once you prove they can't do it, no matter how big their program is, then you can claim the prize.
So basically, the summary of this talk is there's a way to become millionaire by doing this.
Yes, that's right. So this is like, is this the easy way to become a millionaire? No, this is like the hard way. Probably you could just sell something.
Before taxes also.
Right, exactly. So after taxes, maybe 700,000. So do you guys have any questions, or do you guys feel like you understand the problem? It's a set of computable functions. Oh, now there's one more thing. In a real life problem, a lot of the inputs you might input in or don't really correspond to anything. They're kind of not syntactically correct. So that's another thing. When people casually talk about an NP complete problem, usually there's ways of encoding the problem. They're supposed to lead to specific answers. Then there's a lot of just syntactically incorrect inputs, Well, now we don't have a well-defined function because nobody told us what we're supposed to do with this. You should write your program to detect those and zero those out, and then think of that as the function that they're calling incomplete. So what is an incomplete problem? It's really a function that's so hard to compute that, using non-deterministic machines, that if there was a deterministic one that was compute the function fast, that would be, they definitely are equal. So there's a lot more I can say, but I only have 50 minutes. I already went over 5 minutes.
Do you want to give us maybe another talk about this later?
I actually wrote a second talk here. Yeah, I could. I actually wrote a second talk that's explains why some of the functions are not computable.
Maybe we can, not today, but maybe
Okay.
we can do another one.
I can do it anytime. Would you actually come back? Y'all like, yes. But,
Especially after you solve the problem.
yeah. So actually, what I've been trying to do to solve the problem is I'll take a problem that's incomplete, right? That's known to be hard, and then what I'll do is I'll make the problem simpler. Now, the moment you make that problem simpler, unfortunately, you may have just left incomplete, right? And now you're not in the incomplete world. So my strategy is I find the famous incomplete problem, I make it a lot simpler, so that it's just simpler to try to solve. Then I just assume it's probably incomplete. I just guess. And then once I can show that even that simpler problem is probably so hard that you still can't solve it, then my intention is to go offer to share half the prize money with an expert that could probably in 5 seconds say, oh yeah, obviously that's incomplete because these 50 theorems that I've never heard of because I'm not an expert. Right, so that's my strategy. It's like I make problems simpler, but I still try to make sure they still seem pretty gosh darn hard, simpler so I can think about it more. So for example, you wouldn't think that trying to add numbers together, unless they're trying to add them to equal a bunch of ones, you wouldn't think that has anything to do with taking a bunch of Tetris pieces. Let's say you have tons of Tetris pieces, and somebody says, you're allowed to place this Tetris piece in this part of the board, you're allowed to place this Tetris piece somewhere here. They give you tons of restrictions like that, right? And then they say, could you fill the whole board solidly with these Tetris pieces that don't overlap whatsoever? Doesn't that seem like it'd be a problem where if you want to solve that, you just have to almost try everything because everything you do over here could easily affect, a mile away what you're allowed to put over here, right? Does this problem strike you as having any connection at all to just adding numbers together? What do y'all think?
No, I have no idea.
No idea. Well, what you could do is for every digit here, you can think of every digit, these numbers as corresponding to a location. And then you could build up your Tetris pieces as you could put ones in just specific locations that would, you can put them adjacent to each other. So in your number, you can make sure there's 4 ones that correspond to those positions. And then you can do that for tons of pieces. You can make tons of copies of this number if you'd like the person to be allowed to move it places, which to make the problem harder, you probably want to, put those 4 ones in other positions the Tetris piece could be legally equal to, right? And then try to figure out if that sub adds all ones. Well, that's exactly the same as trying to cover the board, because covering the board means every square has a corresponds to a number that has a 1 in one space, nobody else has a 1 in that space. So when you add them, they should all be ones. When I started trying to solve, this is a problem I've tried to solve hard for a long time, this kind of Tetris piece problem. And it just makes me feel like, surely you cannot solve that efficiently. I mean, surely. But the more restrictions you put on these Tetris pieces, the more the input size grows. And that's giving the program longer. It's now a little longer to try to sort that out. So anyway, there's been dozens of these problems, which I've tried to turn into other problems. And I've done that enough times where it's getting to become pretty obvious to me. Yeah, surely, for some problems, you pretty much better try everything. And everything means you cannot solve it very fast. The computer can tell, go try everything. And it's like the computer will take an awful long time to try everything.
So NP complete is, it's like, these are well defined, right? People know these problems can be solved. NP, right?
Right, so NP complete problems are in the class NP. They're computable by non-deterministic Turing machines in polynomial time. And then they're also to have the special property that if any one of those NP complete functions were also P, it turns out that's provable that the whole class of problems is NP. It's amazing that anybody ever figured that much out, but
But I mean, the hard part is that you don't know whether you couldn't find a P, I mean, for the same problem, you couldn't find, whether you can find a P algorithm, right, basically, right?
Yeah,
Deterministic, in polynomial time. Right?
yeah, that's right. So you pick one of these NP problems, and then since these two classes, I bet they're not equal, you need to somehow convince someone they're not going to be smart enough to take your problem and be able to do much more with it. And just try every
So
possible
if
solution.
you're smart enough, you can find a P algorithm, then you prove they're equal, right? Basically, right?
Yeah, but there's just no way. So what you're really trying to do is show somehow it's just no matter how clever you are. Think about if you were trying to run through a maze and you couldn't see the maze at all. Would you kind of have to go through the maze in every possible way? Yeah. However, if you knew the maze kind of was in the square and you knew the exit was sort of here, and let's say you went all the way across here, there's no ways to go this way, except for maybe one way. Now all of a sudden, do you really need to try these ways? If you see a line that cuts the base in half, all of a sudden you can kind of infer, I don't need to try any of these ways, because once I go this way, there's no path that returns to this way, other than a path I can already see.
For your strategy, you're trying to simplify the NP problem, right?
Yeah.
But it's possible that when you simplify too much, it's not NP anymore.
It's possible, but I'm just assuming I'm not getting that part wrong. I'm just crossing my fingers.
So you let's say you got a simple case. Will somebody else, maybe like an expert from them, may be able to prove that it's still NP, right? Like you simplify it. It's possible it's still NP, right?
Yeah, that's what my strategy is, to see problems.
But say for the simplified version, what do you want to do with that version? You want to try to find a P algorithm?
In my case, I'm trying to prove the problem is so complicated, people are not going to be able to do much except try all possible solutions, and therefore they can't run an efficient program. Like I said, kind of like a maze, on the surface of maze seems like you have to try all possible paths, but the problem is, if you know something about where the exit is, and let's say there's a path all the way through, and there's a path leading to the right, some to the left, well, some that lead to the left may eventually come back around, then you can take a path to the right. However, you don't need to consider any of these because the base was cut in half. That structure you can exploit to not try all possible paths. Almost all math problems have that sticking point. It's like you think you made it really loose and people are just gonna have to try everything, but everything has structure. If it's mathematically defined, right, all of a sudden there's all kinds of exploitable structure. And that's actually what mathematicians are just really excel at, is exploiting little structure in a problem to say, oh, because we know this, we know all this other stuff. So that's the trickiness of this problem, is somehow you have to make something that has structure, and you're trying to make it as unstructured as possible so the person doesn't solve your problem very easily. But then it has structure just by virtue of it. It's a problem.
Is it possible to make it?
I'm gonna let you guys go. Yeah.
Make it axiom, like let's say axiom P does not equal NP. What we do, we set it as axiom. Would that be? And then what can we get from there? Like we just say that we assume that it's not equal.
Oh yeah.
Give us something new.
I have no idea what all the consequences are. Yeah, I don't know. So, okay, sorry to drag you guys over, but do you guys have any other questions? Or
yeah, do you guys have any questions?
did you guys have any questions to begin with, or did I just make up my own questions? I'm like, let me tell you, you can do this and this. It's a really good problem. So I'm glad I tried to solve. I've been on this problem for about 2 years, and I'm glad I tried to solve it, but I'm about to move on for a while. Because yeah, it's I can see now why it's such a famous problem. So I feel like I've conquered it. I understand why it's so hard. And now, I'm going to keep working on it, but I'm going to copy on also into something else.
So you guys are interested in I have another talk. It's another talk. Yeah. Maybe like what about 2 weeks from now, or 1 week next week, or. So you're definitely, you can give another talk, right? Continue on this stuff, right?
Yeah, I'm giving a bunch of exams next week, so preferably 2 weeks, 4 weeks.
2 weeks, 2 weeks or 3 weeks or something.
Yeah, whatever.
Okay, we'll figure out another time then.
Yeah, so thanks for coming. I'll make sure the next talk's only 40 minutes to like balance this hour long.
Okay, let's thank Dr. Michael.